When we introduce to you guys a conventional roller coaster, we say that it's this first drop that determines whether or not you can make it through all the successive bumps that you would encounter along the way. Now that being said, we did not consider anything that involved the loop. So if you take a look at a loop and then let's say we applied that same type of thinking to the loop, basically this would not be enough to get us through the loop. Point being here is that as you travel through the loop, if you made it back to this height here, your velocity would be 0, and what would end up happening is that you would just fall straight down. So we've determined from the circular motion unit that our speed needs to be equal to radical GR, where R is the radius of the loop, in order to safely make it through that loop. So what ends up happening is we can model that problem and derive an expression for what the minimum height we need to release from this. So here's our loop of radius R. We're going to release from some height above it. We'll call it H. And essentially, we know our V here. We're going to release from rest here, V equals 0, and our V here is radical GR. And we also know the height of the loop in terms of R, and that's going to be important because that's going to get us our height in terms of R for the height over here. So our height here of the top of the loop, our position, is at a height of 2 times the radius of the circle. So when we model it that way, we can get this expression using a conservation of energy expression. So when we say that our kinetic and potential sums have to be equal at both points here, we're starting from a height of mghi, which is that. I'll label this as hi as well. And then we're releasing from rest, so our kinetic energy 0 there. At the top of the loop, we're at a height of 2r, so it's mg2r is the potential energy there, and the kinetic energy would be 1/2 m, and then the velocity we just said has to be radical gr from the circular motion chapter, and then we square it because it's 1/2 mv squared. And pretty quickly this comes together, and you cross out your m's, mass doesn't matter here, and then we have hi equals 2gr, and then when we square that, you get radical gr squared, which is just gr, so we have a 1/2 gr here. Turns out g cancels out as well. This would work on any planetary body, and we see exactly how much higher we have to be in terms of r here. So you get a 2r plus 1/2 r. You can call this 5/2 r, or if you wanted to, you could simply write 2.5 r, which is clearly higher than that. So it's a full half, it's a 0.5 r above the top of the loop.